Welcome back. In this third video in our trig substitution integration series, we're going to do an example where we use x equals a sine theta. All right, so I have included in here a picture from what we discussed in the first video where we talked about how and why these trig substitutions are going to work. So you'll notice this is 9 minus x squared, which is in the same form as a squared minus x squared. So that lets us know we're going to use this sine substitution. And it may help you to think about this as sine theta equals x over a. So considering theta, my reference angle, is in the lower left corner, and that sine is opposite over hypotenuse, we have x over a, and then by the Pythagorean theorem, we can determine this adjacent side at the base of my reference triangle. So considering that, and since we have this patterning and we know we're going to use sine theta, we have to determine what our a value is. And remember, our a value is some constant squared. In this case, a is going to equal 3. So we're using that sine of theta equals x over 3. Now, remember, when we are dealing with inverse sine, we have a range restriction. And the range restriction for inverse sine is a closed interval between negative pi over 2 and pi over 2. Looking at this, then, I'm going to say, well, x equals 3 sine theta. And since x equals 3 sine theta, dx, d theta, equals 3 cosine theta. Now remember, we like to treat that as a differential. Move that over here. So I've got dx is 3 cosine theta d theta. So looking at what I have a substitution for x and a substitution for dx. And you'll notice I have this x in the denominator as well. Before I sub 3 sine theta in for that x value, I prefer to do a little calculation and determine what 9 minus x squared is first. So in this situation, 9 minus x squared, that's equal to 9 minus 3 sine theta squared, or 9 minus 9 times sine squared theta. Factoring out that 9, we have 1 minus sine squared theta. And 1 minus sine squared theta by the Pythagorean theorem, or Pythagorean identity, is equal to cosine squared theta. So I've got 9 cosine squared theta. So I know what I'm going to plug in for my radicand, I know what I'm going to plug in for this x value, and I know what I'm going to plug in for my dx value. So let me scroll down a little bit. I'm going to rewrite what we started with. We have the integral of x squared dx over the square root of 9 minus x squared. So all I've done here is to rewrite my original integral just so we can see that substitution. So x, we say, is 3 sine theta, and that needs to be squared. dx is 3 cosine theta, d theta, over the square root of 9 cosine squared theta. So we've created all of our substitutions based off the initial condition for the substitutions that we set. At this point, we need to simplify. So we have our integral 3 squared times 3, that's 9 times 3, or 27, We've got 27 sine squared theta times cosine theta d theta over, and the square root of 9 is 3. The square root of cosine squared is just cosine. So I have 3 cosine theta. And when we write that, technically we need absolute value bars. However, because we are specifying that theta has to be in the closed interval from negative pi over 2 to pi over 2, we can drop those bars, and I can just write 3 cosine theta in the denominator. So you'll notice we have some values that cancel. Cosine theta over cosine theta will go away, and 27 over 3 will become 9. So this is 9 integral of sine squared theta d theta. So this is sine to an even power. And when we're dealing with those even powers of sine, we like to use a double angle. So the double angle identity we use is that sine squared theta equals 1/2 times 1 plus cosine of 2 theta. And I wrote plus. That is a minus for sine. It's a plus when we have cosine. So this now gives me, I have 9 halves, just pulling that 1/2 in front, the integral of 1 minus cosine of 2 theta d theta. At this point, I can integrate each of those two terms. I have 9 halves. The integral of 1 would be theta, and the integral of cosine 2 theta is sine 2 theta over 2. So I'm done with my integration here, but we need to clean this up. All right, so at this point, we've found our integral. It's in terms of theta. We need to go back to having it in terms of x. So there's only algebraic manipulation at this point. One thing is when I go back to my previously organized, the way I set up my reference triangle, we had x, 3, and the square root of 9 minus x squared. All right, we said that sine of theta is x over 3. Now, I don't know what sine of 2 theta is, so I need to use an identity to reduce that sine of 2 theta out. One identity that I can use is a double angle identity. Sine of 2 theta is 2 sine theta cosine theta. So now I have 9 halves theta minus 2 sine theta times cosine theta over 2 plus c. And of course, those 2's are going to cancel. So I have 9 halves theta minus, I'm distributing 9 halves sine theta cosine theta plus c. So you'll notice I have sine theta, and I know what sine theta is. It's going to be x over 3. Cosine theta, in regard to my reference triangle, is adjacent over the hypotenuse. So cosine theta is the square root of 9 minus x squared over the hypotenuse 3. And then we also need to figure out a way in order to write theta. I can isolate theta in this sine theta equation and say that theta equals inverse sine of x over 3. So if I make these 3 substitutions, I will be completely done with my problem. I end up with 9 halves of sine inverse of x over 3 minus 9/2 times x over 3 times the square root of 9 minus x squared over 3, and then plus our arbitrary constant c. So as I work through this, there's just one step. I can reduce the 9 and those 3's out, so I'll just tidy this up just a little bit. 9/2 times sine inverse of x over 3 minus x times the square root of 9 minus x squared over 2 plus c. That's the final answer here for this integration. So just to recap, in this video I did a integration using a trig substitution, which is different than integrating a trig integral, which was what we did in the previous section here. So we did an integration with a trig substitution, and I used the sine substitution. So we have one more video in this series, and that will be using the secant substitution. As always, email me if you have any questions.